The search for planets beyond our solar system has brought a discovery of historic significance. A planet slightly larger than Earth orbiting a red dwarf star called Proxima Centauri. At just over 40 trillion kilometers from the Sun, Proxima Centauri is our closest stellar neighbor. In the coming years, astronomers will probe its dim light to understand the tiny world that circles it. Does this planet have a climate? Flowing water? Even life? What will it take to get a closer look? To launch our first interstellar journey to the pale red dot. On a clear night far from city lights, you can see around 4,500 individual stars. These bright stars are spread throughout our region of the galaxy to distances many thousands of light years away from Earth. Four of them lie within 50 light years of Earth, within the neighborhood of our Sun. Nestled among those bright stars are some 2,000 others that are so dim you need a high-powered telescope to see them. They all sit within the local bubble, a region probably cleared of gas by an ancient supernova. Our little corner of this bubble is occupied by a handful of well-known stars. They include 61 Cygni, 11.4 light-years from the Sun; Epsilon Eridani, 10.5 light-years away; Sirius, the dog star, at 8.6 light-years away. Then there's our nearest neighbor, the triple star system Alpha Centauri, 4.4 light-years away. Alpha Centauri A and B are a pair of Sun-like stars. Proxima Centauri is gravitationally bound to this pair. At 4.2 light-years away, this red dwarf star is the closest star to our Sun. Astronomers have been carefully monitoring the Alpha Centauri system as part of an intensive campaign to find planets in the solar neighborhood. The study began at the European Southern Observatory in the mountains of Chile in 1996, when astronomers began looking for a slight change in the color of nearby stars. Called a Doppler shift, it's similar to the way the sound of a train whistle distorts as it races past us. The same effect can be seen in the wavelength of a star's light if a planet tugs it slightly toward or away from us. This wobbling motion causes the star's light to stretch toward the blue part of the spectrum, then the red. The instruments that measure this wobble are so sensitive that they can detect a star's movement down to speeds of just a few meters per second. The search seemed to bear fruit in 2012, when astronomers reported tantalizing hints of an Earth-sized planet circling Alpha Centauri b. Excitement spread, Unfortunately, the data did not hold up to further observation. Still, it fed the hope that we'll one day stumble upon a world like Earth in our own backyard. With oceans, a robust magnetic field to shelter it from solar winds, a moon to stabilize its orbit, and even creatures who reveal their presence by beaming electronic signals into space. In 2016, Alpha Centauri was back in the news. Astronomers announced they had found evidence of a planet orbiting Proxima Centauri. They confirmed this discovery with data from a network of telescopes around the world. The newly discovered planet, they said, is at least 1.3 times the mass of Earth. It occupies a close orbit, swinging around its parent star every 11.2 days. Surprisingly, that puts it within the star's habitable zone. That's the region around a star in which temperatures are in the right range for liquid water to exist on a planet's surface. If the planet is much closer, the heat from the star would boil the water away. If further out, the planet's water would freeze solid. In our solar system, Earth sits squarely within the habitable zone, which extends out toward the orbit of Mars and in toward Venus. Our star is roughly 10 times the radius of Proxima Centauri. Because Proxima has only 2% the luminosity of the Sun, its habitable zone sits well inside the orbit of Mercury. While our Sun's light spans the electromagnetic spectrum, Proxima's light is concentrated in the long wavelength infrared portion. That means that if you were to visit the planet, your eyes would see a world draped in green and red. There is enough solar heat striking the planet to allow liquid water to flow. However, it's still a matter of debate whether Proxima b and other planets like it could ever support a climate, much less life. And yet, small dim stars like Proxima Centauri may offer our best chances of finding a habitable planet in the solar neighborhood. The Kepler Space Telescope was launched in the year 2009 with a major goal of finding small rocky planets that could resemble Earth. Pointed at a patch of sky in the direction of the Cygnus constellation, the telescope was used to measure the brightness of 150,000 stars every 30 minutes. Kepler uses what's known as the transit method. When a planet passes in front of a star, it causes the star's light to dip slightly. The initial survey picked up planets that have the most pronounced effect on the star's light. Large, heavy worlds that whip around their parent stars every 5 to 50 days. Some are large, rocky worlds called super-Earths. They most likely formed within warm dust clouds left over from the formation of their parent stars. Some of these are so close to their parent stars that they're most likely emblazoned with lava. Others are gas giants that migrated in from the outer solar systems, drawn by the gravity of their star. In the closest orbits, solar heat and particle winds are slowly stripping them of their thick atmospheres. In a more recent survey, scientists used Kepler to focus on 42,000 sun-like stars. In a statistical study based on this sample, they found that 22% of these stars have planets about the size of Earth, with an orbit in the right range to support liquid water. If this estimate is right, then our galaxy potentially harbors around 9 billion such planets. Statistically speaking, we can expect to find at least one within 12 light years of Earth. That doesn't mean it will support life. Venus sits in the inner edge of our habitable zone. It's enshrouded in a thick atmosphere dominated by a runaway greenhouse effect. There is no liquid water or life on its surface. Mars, at the outer edge, has lost nearly its entire atmosphere. And today, the planet is cold, dry, and barren. To improve their chances of turning up an Earth 2.0, scientists are intensely monitoring the much larger population of dim stars, like Proxima Centauri, that are nestled among their brighter cousins. These so-called M stars, or red dwarfs, range from 1/2 to 1/20th the mass of our Sun and make up 76% of all the stars in our galaxy. Interest in these stars was spurred in part by studies of the star Gliese 581, 20 light-years away in the southern constellation of Libra. The planet hunters of the European Southern Observatory first deduced the presence of Gliese 581b, a planet 16 times the mass of Earth. At a distance of only 6 million kilometers from its sun, it's well inside the habitable zone. It's flanked by two others, planets C and E. Planet D, still unconfirmed, is at the outer edge of the habitable zone, about 33 million kilometers from its sun. It receives only 30% of the light that Earth gets from our sun. It may be an icy world that migrated in from the outer solar system. Gliese 581g, also unconfirmed, is thought to lie at the inner edge of the habitable zone. At twice the mass of Earth, it might have a chance of supporting liquid water. But this planet is nothing like Earth. Our Earth spins on its axis, 366.25 rotations for every turn around the sun. With the exception of polar areas in opposing seasons, every part of the Earth sees the sun every day. That helps distribute solar heating while generating the winds and ocean currents that define our global climate. Earth is far enough from the sun that the gravity of the star doesn't exert much influence on its spinning motion. In much closer orbits, Gliese 581g, like its cousin, Proxima b, would likely have fallen into what's known as gravitational lock. That means that only one side ever faces the sun, while the other side faces out into the darkness of space. The traditional thinking is that if there is water on this planet, it is most likely evaporated from the light side and become impounded as ice on the dark side. That view began to change in the late 1990s when NASA scientists simulated the atmosphere of a locked planet. They found that global wind patterns could develop and transport heat to the dark side. Scientists at the California Institute of Technology sought to test this finding on our planet. Working with a supercomputer program normally used to predict our climate, they simply turned off Earth's rotation. The team placed the subsolar point, the region facing the sun, just off the coast of South America. Evaporation on the sunny side sent air rising up in storms and pushing back over the poles to the dark side. As a result of this poleward flow, Alaska experienced summer all year round. Land masses on the dark side, including Europe, Asia, and Africa, went cold. Remarkably, over the 5 decades of the simulation, the oceans retained enough heat to stay clear of ice. On the light side, large parts of the Western Hemisphere dried out, turning to desert. But if you pitched your tent at the subsolar point, you'd find a hot and rainy climate that resembles this place, the island of Kauai in Hawaii. Its highest point is Mount Waialeale. That's Hawaiian for rippling or overflowing water. Known as the wettest place on Earth, the summit averages 11 meters of rain per year. How would life adapt to sunlight all the time? Plants depend on light to drive photosynthesis, a process that combines CO2 with water to produce sugars needed for growth. They use the day-night cycle to maximize this process, to tune their growth rates, and to take in more carbon dioxide. In polar regions, some plants are known to thrive in periods of extended sunlight in summer. So, if you take away the night, there is a chance that life could adapt. On Earth, its ability to do so draws upon hundreds of millions of years of evolution in a diverse global biosphere, dependable day-night cycles, and moderate temperatures. The question is whether a climate could develop in the first place on a locked planet. A team from the University of Chicago sought to answer this question by simulating the different states such a planet could take. The most promising scenario, assuming abundant water and carbon dioxide, is a planetary type called an eyeball Earth. This planet is gravitationally locked, with an icy dark side and a sunny light side. In between is a transition zone where the sun is always low in the sky. Here, the ice gradually fades into a warmer, sun-filled realm. In this representation, the subsolar point is flanked by a continent and areas of open ocean. What could tip the balance toward habitability, according to one recent study, is the planet's ability to maintain a cloud cover. If warmth from the light side flows to the dark side, it can moderate temperatures and allow ice to melt along the transition zone. As water flows back to the light side, it evaporates, fueling more clouds. Clouds further moderate temperatures by reflecting solar radiation back to space, while also contributing to a greenhouse effect that holds heat in. But even if Proxima b has all the right characteristics, it would still face formidable obstacles to nurturing life. Proxima Centauri, for example, is known as an active M5 star that currently emits intense flares every 10 to 30 hours. For a planet in such a close orbit, blasts of radiation can split water molecules in the atmosphere. That allows hydrogen to waft into space and oxygen to bind to rocks on the surface. This process can strip the planet of water. To find out what state Proxima b and other nearby planets are in, astronomers will turn to a series of powerful new telescopes coming online over the next decade. The long-awaited James Webb Space Telescope, slated for launch in 2018, represents the next generation of great space observatories. With a segmented primary mirror that is almost 3 times larger than that of Hubble, the James Webb will capture the trickle of photons coming from the early universe and allow scientists to finally parse the light of nearby stars. The W-FIRST telescope is slated to launch in the mid-2020s. With the resolution of Hubble, W-FIRST will take in light from a region 100 times larger. Its main targets include distant exploding stars, used to measure the expansion of the universe, along with planets interacting with stars in nearby solar systems. W-FIRST will bring a powerful new technique to planet hunting. If a star passes in front of another star, it acts as a lens, brightening and dimming in ways that can betray the presence of planets. These new instruments promise an unprecedented view into the light of nearby stars. By deploying coronagraphs to block the light of parent stars, they'll be able to pick up light reflected by planets. This technique will allow scientists to measure surface temperatures, as well as distinguish between a planet's light and dark sides. They can also use a spectrograph to detect atmospheres and to look for chemical signatures of life. There will be no shortage of targets. The Belgian TRAPPIST telescope turned up a surprising cache of planets circling what may seem an unlikely place. At 40 light-years away, TRAPPIST-1 is a cross between a large Jupiter-like planet and a star. This ultra-cool dwarf emits only a tiny fraction of the light of our sun. Astronomers used the transit method, using their telescope to detect slight dips in the light of the star as planets passed in front. Then, they followed up with an intensive program of observations from telescopes on the ground and in space, including NASA's Spitzer Infrared Observatory. They found 7 planets bunched together in orbits close enough to be tidally locked. At least 3 of them are at the right distance and temperature for liquid water. Planet F is the most likely to harbor life. It's 1.3 times the mass of Earth, with an orbit lasting 9.21 Earth days. Gracing its salmon-colored skies are at least 6 sister planets, all as large or larger than our full moon. Here, you'd get 200 times less visible light than on Earth. Instead, the star bathes the planet in infrared light. It delivers enough energy to potentially power a climate. A broad initiative has begun to follow up on the flood of discoveries in this golden age of planet finding. Ground-based telescopes are now being outfitted with a new generation of imaging devices. At the European Very Large Telescope in Chile, for example, scientists are installing a new infrared imager and spectrograph specifically with Proxima Centauri in mind. This effort is being done in collaboration with a whole new player in the space sciences. Breakthrough Initiatives is a privately funded 10-year, $100 million plan to search for extraterrestrial intelligence. It hopes to lay the foundation for spacecraft missions out into our solar neighborhood. Any interstellar mission must confront the ultimate obstacles to space exploration: distance and time. The New Horizons probe recently made the 4.8 billion kilometer journey to Pluto, arriving in 9.5 years. At its top speed, 84,000 kilometers per hour, it would take 54,400 years to travel the 40 trillion kilometers to Proxima Centauri. The spacecraft Voyager 2 would take even longer, 70,000 years, traveling at 69,000 kilometers per hour. In a sense, though, Voyager paves the way for future interstellar treks. Voyager's designers imagined these twin spacecraft would far outlast human civilization. With their current momentum, they could wander the galaxy for millions, even tens of millions of years. What if intelligent beings detected and captured one of them? Its handlers famously placed a trove of information aboard to educate these alien captors. That includes information about planet Earth, its people and culture, including images and sound recordings. It also offers a way to find us, in case anyone decides to follow up. This symbol is a system of celestial GPS coordinates. It places Earth at the junction of radio beacons emitted in this part of the galaxy by pulsars. They're a type of ultra-dense star that spins rapidly, giving off pulses of radio energy. Like sailors who once used a sextant to navigate by the stars, a future spacecraft could use pulsars to orient itself in the featureless expanse of interstellar space and navigate to a distant target. NASA engineers are now designing a prototype space sextant to be tested aboard the International Space Station. As the station orbits the Earth, the instrument locks onto the light of distant pulsars. In 1990, as it sped toward the outer regions of our solar system, the Voyager 1 spacecraft turned its camera back toward Earth. From 6 billion kilometers away, it sent back an image of the pale blue dot we call Earth. It was a humbling reminder of the rare and precious world that has nurtured us. Today, we're looking out beyond our solar system to a planetary destination illuminated by the dim light of its parent star, Proxima Centauri. But can we realistically get anywhere near this pale red dot, over 4 light years away? Interstellar flight has long been a staple of science fiction. Humans from technologically advanced future civilizations routinely board starships for remote corners of the galaxy. For some real-world scientists, the challenge of crossing the immense voids of time and space has led to whole new lines of investigation. Propulsion engineers have submitted proposals for the development of advanced spacecraft. Powered by nuclear fusion, antimatter, the gravity of tiny artificial black holes, the strange physics of warp drive, and specially designed sails to be pushed along by solar winds. Or by giant lasers. This is a surprisingly old idea. The 17th century astronomer Johannes Kepler observed comet tails being blown by what he thought must be a solar breeze. He served up an imaginary scene to his friend Galileo of ships powered by sails adapted to the heavenly breezes. In 1873, James Clerk Maxwell showed that light exerts pressure, an idea that motivated modern space sail designs. NASA engineers were able to put this idea to the test during the Mariner 10 mission to Mercury in 1974. They used the pressure of sunlight on its solar panels to stabilize its flight around the planet. Modern mission designers have warmed to sails because they don't require enormous amounts of fuel. Recent advances in the miniaturization of electronics and strong, light new materials are giving the idea new currency. And now, the discovery of planets in our solar neighborhood offers a range of potential interstellar targets. A new plan announced by Breakthrough Initiatives, called Operation Starshot, will use sails to target the closest of these targets, Alpha Centauri. The Breakthrough Plan calls for an array of powerful lasers installed on a high plain or desert in South America. In these dry, high-altitude locations, the laser light is less likely to be distorted by moisture in the atmosphere. The lasers would draw power from a large dedicated generating plant. The idea is to deploy a fleet of ultra-thin sails in Earth orbit, ready for launch. Each one is outfitted with a miniature command center, 2 centimeters wide and weighing only a gram. This tiny chip contains sensors, shielding against cosmic radiation, and a radioactive power supply. Add to that mini thrusters, a communication system, and a camera. This light sail is relatively small, 4 meters wide, and perhaps only a few hundred atoms thick. It would have to be tough enough to withstand the impact of a high-powered laser. The launch array locks onto its target, on a line of sight to Alpha Centauri. Ignition. And liftoff. The next day, with a charge restored, the array is ready to fire again. The spacecraft quickly reaches 20% the speed of light, passing Saturn within hours, and Pluto in just a day or two. For most of the journey, the spacecraft go dormant to preserve power. Periodically, the lead craft wakes to perform guidance maneuvers or to send information back to the next spacecraft in line for relay back to Earth. Finally, in 2 decades' time, the fleet approaches its target, Proxima Centauri. The craft may be able to use the wind of particles coming from the star to slow down. As each flies by, they turn to face the planet Proxima b. The camera captures the scene. Perhaps, as it turns around, we'll see our sun, a brilliant white dot framed by the galactic landscape. As for the pale red dot and its planetary companion, what will we learn from the morsels of information that make it back to Earth? With luck, we'll find that Proxima b is having its day in the sun, with the development of a global climate that perhaps has nurtured life. For some on our own planet, the news that a spacecraft has arrived at an alien world will no doubt pass overhead. In the ongoing daily rush of technology, crisis, war, consuming, and escape. For others, that day will be filled with a sense of humility, fascination, and wonder.